Okay, students, so let's start with the past papers of waves. This is applicable for both O levels and IGCSE physics. Water waves are transverse waves. Underline two other examples of transverse wave, seismic S waves and X rays is your example. Okay, let's move on to part B. Figure 5.1 shows a wooden bar and a glass block in the ripple tank. The depth of the water in the tank is less than the height of the glass block. Okay, so this is your wooden bar. Let me highlight it so at least you guys know what is your wooden bar. This thing is your wooden bar. What is your glass block? Your glass block is this thing. This thing. It is erased here. 1 second. Yeah, this is your glass block. Simple as that. This is your glass block. Both the glass block and the wooden bar were given in the question itself. Okay. So let's further move ahead. The wooden bar moves up and down. This yellow thing moves up and down every 0.15 seconds. Okay. So basically, the time period is given to you to create the crest. The speed of the water is this. You have to calculate the frequency in wavelength. Frequency is what? 1 over time period. 1 over 0.15 will give you your frequency. Your frequency comes out to be what? Let's calculate that. 1 divided by 0.15. This comes out to be 6.7 hertz. Okay. And the speed of water wave is this. Can you calculate the wavelength? Yes, V is equals to F lambda. Speed is 27 divided by the frequency 6.7. You will get your lambda. So, by your answer, this gives you a wavelength of 4.05 centimeters. 4.05 centimeters. So you have both of them. You have the frequency as well. You have the uh, wavelength as well. So everything gets done here. Let's further move ahead. The wave diffracts at the right hand edge of the glass block. On figure 5.1, draw two crests after they pass the glass block to show the diffraction. Okay. So we have to draw two crests here. How can we draw two crests here? The waves are diffracting around an edge. So whenever waves diffract around an edge, you make circles like this and you make sure that this lambda wavelength is equals to this lambda. The wavelength remains same. Okay. Let's further move ahead. And if you want to see a better diagram for this, I have attached a diagram in the notes as well. The previous lecture of notes, you can view that. Describe how a wave with a smaller wavelength is made with the wooden bar. If you need a smaller wavelength, what do you need to do? Velocity is equal to frequency over lambda. Velocity is a constant thing. Velocity is a constant thing whenever you are making a wave. Okay. So if velocity is constant, frequency and lambda will be what? Inversely proportional. If you want a smaller lambda, your frequency should become large. So what will you say? Move the wooden bar faster. Move the wooden bar faster, or you can say with more speed. Describe how a decrease in wavelength affects diffraction. Diffraction increases as your wavelength decreases. Diffraction increases as wavelength decreases. Obviously, I am writing in a very shorthand format. You need to write the complete statements. Let's move ahead. A water wave in a ripple tank diffracts as it passes through a barrier through a gap in a barrier. Figure 7.1 shows a drawing made by a student of the crest in the pattern. Okay. State one way in which the student's drawing of the crest is wrong. Can you see the lambda here wavelength is not matching the lambda of these crest is not matching the lambda of these crest. So you will say wavelength before before and after diffraction are not same. Before and after diffraction are not same. Are not same. Let's move on to part B. The gap in the barrier is now smaller than the wavelength as shown in figure 7.2. Okay. Complete figure 7.2 with at least 3 crests to show the new diffraction. So you will make 3 circles like this. And what is the thing that you need to take care of? What is the thing that you need to take care of? Anyone in the chat? You must make sure that the wavelength here, this lambda, must be equal to these lambdas. And also you can draw it with a compass as well. I have been pretty lazy and just drawn the circles like this. Okay, in one part of the ripple tank, the water wave has a speed of 6 centimeters per second and a wavelength of 2 centimeters per second. Okay, 2 centimeters. So this is your lambda, this is your speed. The wave then passes into a shallower region. Okay, the speed of the wave in shallow region is this. Describe the term wavelength. Distance between two consecutive consecutive consecutive. I hope I have written consecutive. Let me search the spelling of consecutive. Yeah. Yeah. I think I have made a mistake. No, I have written it correct. Yeah, I have written it correct. So distance between two consecutive in phase points is known as wavelength or lambda. Okay. Calculate the frequency of the wave. You have to calculate the frequency of the wave. We will apply V is equals to F lambda. Velocity is what? 6. Frequency, we don't know. We know the lambda as well. So here comes the lambda. Frequency comes out to be 3 hertz. Simple. Calculate the wavelength of the wave in the shallow part of the region. In the shallow part of the region, the frequency remains same. Do you have the speed? Yes, the speed is 4 in the shallow part of the region. 4 centimeters per second. Can you calculate lambda? V is equals to F lambda. V is 4, frequency is 3, lambda comes out to be what? 4 divided by 3, 1.33 centimeters is your lambda. Simple. Let's move on to the next question. Figure 8.1 shows a ripple tank and the crest of the water wave that is produced in it. Okay, this is the crest of the water is produced in it. The frequency of the water wave is 2 hertz and its amplitude is 3 millimeter. Calculate the number of crests produced in 1.5 seconds. Okay. So first of all, you have to understand what does 2 hertz mean. 2 hertz mean that there are two waves being produced in 1 second. There are two waves being produced in 1 second. Something like this. This is what happens in 1 second. So if 1.5 seconds is happening, if a time period of 1.5 second is elapsing, what will happen? If two waves are getting produced in 1 second, 1.5 seconds will have how many waves? 3 waves. Simple ratio method. So you will have 3 waves in 1.5 seconds. This is 1.5 seconds. Okay. How many crests can you see in 1.5 seconds? 1, 2, and 3. So the number of crests in 1.5 seconds is 3. Let's move on to the next thing. Let's see this. The height of the wave is measured from the level of the undisturbed surface, that is from the mean position. That means the graph will start from 0. The height of the water wave at time t is equals to 0 is 0. On figure 8.2, draw a graph to show the height of the wave at this point varies with time. Okay, how does the height varies with time? We know that the amplitude is 3 and the frequency is 2 hertz. So let's zoom in a bit. Amplitude is 3. What does that mean? This is 2.4, 2.8, 1, 2, 3, 4. 1, 2, 3, 4. Let me correctly see it. 1, 2, 3, 4. Yeah. So 3 will lie somewhere here. Okay. And since your frequency is 2 hertz, that means two waves will be completed in 1 second. That means till here I will have two waves completed. If two waves are completed in 1 second, how much time will it take for one wave to complete? 0.5 seconds, somewhere here. So let's draw the wave. Somewhat like this, and probably here. Let's draw the wave. Somewhat like this. Let's continue this wave as well. This is 3 again. This is 0 again. And this will be -3. So, yeah. Make sure the amplitude in the positive and negative direction is both 3. Let's make 3 here. Let's make 0 here. Let's make 3 here. Let's make 0 here. Somewhat like this. This is your wave. You have to make sure that the amplitude is 3 and -3, and there are 3 waves getting completed in 1.5 seconds. Very, very simple. Let's further move ahead. The frequency of the wave is increased. Describe how the apparatus shown in figure 8.1 is adjusted so that the frequency of the wave is increased. How can we adjust this apparatus to cause the frequency of wave to increase? Move the wooden bar faster. Move the wooden bar faster. Move the wooden bar faster. Simple. Let's move on to part 2. State what happens to the speed and wavelength of the wave as frequency increases. What will happen to the speed? It remains same. However, I have told you time and again v is equals to f lambda. If velocity becomes constant, frequency will be inversely proportional to lambda. If frequency increases, wavelength will decrease. Simple. The apparatus shown in 8.1 can be used to demonstrate refraction. State the additional apparatus needed to demonstrate refraction. Maybe a glass block or a plastic block so that we can vary the depth. Okay. Now the next question is something that students are really afraid of. But let me show you a very easy solution for this. Very easy solution for it. What you can do is you can label that this is the deep region, this is the shallow region. Okay. And let's also mark a boundary here. Mark a boundary here. Let's say this is your boundary. Let's label this as X. You will make all of this with a scale, but since there is no option for scale as well here, and since I'm lazy as well, so I'm not drawing it with scale. Okay, in the deep regions, you will have waves coming like this towards the boundary. Like this. Yeah. These are your waves coming towards the boundary X. Okay. This is your boundary X. Let's write it here as well. This is your boundary. Okay. Waves are coming towards your boundary. And as you are traveling from deep to shallow region, what will happen? What do you think will happen as you travel from deep to shallow region? Your wavelength decreases and your speed decreases as well. Your speed decreases and your wavelength decreases as well. How will you show that? Very easy. Literally the easiest diagram, but I don't know why students get confused here. Your wavelengths will get smaller. Obviously, you will draw it with a scale, then this will be more perfect. Somewhat like this. Can you see the distance between the two wave fronts in the deep region is greater? It is this lambda. And the distance between the two wave fronts here is lambda, small. So this is what you had to show. You had to label a boundary where the refraction occurs. We have labeled the boundary as well. Simple. All clear. Any ambiguities here, you can still ask me in the comments. Okay. Let's further move ahead. Figure 8.4 shows a Also, let me tell you, this diagram is actually given by the examiner. Let me show you another question that has the same diagram. Can you see here? Here we are going from a shallow region to a deep region. You have to flip this. You are going from a deep region to a shallow region. This is what you had to draw. Okay, this is a very good thing. This is what you had to draw in the previous question. This is what you had to draw in the previous question. Please remember this. Okay, it's a very easy mark, so you don't need to lose it. Figure 8.4 shows a connection to the internet made from a remote station A using a satellite above the Earth's surface. Data is sent between stations A and B using microwaves which travel to and from the satellites. Station B is connected directly to the internet using optical fibers. The speed of the microwaves is this. Station A and B are 560 kilometers from the satellite. Okay. So the distance of station A from satellite is 560 kilometers, and the distance of satellite from station is 560 kilometers as well. The speed of microwaves is this. Calculate the time taken for the data to travel from A to B. So time taken will be what? Yes, distance over speed. But this distance will be what? 2 times of 560 kilometer. 560 into 10 raised to the power of 3. Why? Because I am converting kilometers into meters. Divided by the speed, 3 into 10 raised to the power of 8. What does this answer come out to be? Let's calculate. 560 into 10 raised to the power of 3 into 2. Okay. Divided by 3 into 10 raised to the power of 8. What does this answer come out to be? The time comes out to be 3.73 into 10 raised to the power of minus 3 seconds. Simple as that. The same data can be sent from point A to B in a shorter time along the surface of the earth using infrared waves to carry the information in optical fibers. Okay. State one property that infrared waves and microwaves have in common. Both are electromagnetic waves. Both are electromagnetic waves. Okay. Suggest one other advantage of using optical fibers to connect stations A and B. Much more privacy, cannot be hacked. Things like this cannot be hacked. Increased privacy. No interception. So, these are the points that you can write here. Let's further move ahead. Okay, now we have this question again. Figure 10.1 shows a water wave moving from shallow to deep water. Okay, from shallow to deep water, what happens? Your velocity increases, lambda increases. Evident on the diagram, this was your lambda initially. Now your lambda has become this. Okay, your lambda has increased. The wavefront shown represents the crest of the wave. Okay. The water wave is made by dipping a wooden bar up and down. The bar makes 10 complete up and down movements in 5 seconds. Okay. Determine the wavelength of the wave in the shallow water. We have to determine the wavelength of the wave in shallow water. So if you can notice, this is 1 lambda, this is 2 lambda, this is 3 lambda, this is 4 lambda. So 4 lambdas have a distance of 12 centimeter. Lambda will have a distance of what? 12 divided by 4, that is 3 centimeter. Lambda is 3 centimeter. Okay. We have to calculate the frequency as well. Okay, that's easy as well. 10 oscillations are completed in 5 seconds. How many oscillations will be completed in 1 second? 2. 2 hertz is your frequency. Determine the speed of the water wave in the shallow water. We have to determine the speed as well. V is equals to F lambda. Okay, what is your frequency here? 2. What is your lambda here? Your lambda is 3 centimeter. Your speed will come out to be 6 centimeters per second. Let's further move ahead. On figure 10.2, draw the line to show what happens to the wavelength, the frequency, and the speed of water as it enters deep water. So wavelength increases, frequency stays the same, speed also increases. Simple. The direction of the boundary is now altered. Okay, the waterways now enter the deep water from the shallow water at an angle as shown in figure 10.3. Okay. On figure 10.3, draw the wave fronts in deep water. Again, you are going from shallow water to deep water. What have I told you initially? From shallow water to deep water, your wavelengths increase, velocity increase. But since this boundary is tilted, we will have to show one more thing here. Let's first of all make normal here. First of all, let's make normal here. Something like this. Yeah, these are your normals. Okay. What will happen here? As you are going from shallow water to deep water, what will happen? Your waves will start to bend towards the normal. Oh, something like this. Your waves, let me zoom in. Your waves will start to bend towards the normal. Somewhat like this. Obviously, you can draw much better lines than me, but I hope you get the point. The waves start to bend towards the normal. One second. Let's draw it in a neat manner. Oh, let's do it like this. The wave starts to bend towards the normal. Something along these lines. Yeah. Can you see the wavelength is also increasing? Obviously, if you draw it with a scale, it will be much more better drawing, and you have this drawing in the notes as well. You can refer to that as well. White light is made of different colors. State the name of four of the colors in the visible spectrum and place them in the order from the smallest wavelength to the largest wavelength. Okay. We know violet, Vib, Gior. We know this acronym. Red has the largest wavelength, violet has the smallest wavelength. So let's place red here. Let's place violet here. Let's skip indigo. You can write indigo here as well, no problem. But I am writing just the colors that are pretty familiar to everyone. Let's see this. A normal beam of white light can be split into different colors. Okay. Figure 10.1 shows rays of white light emitted from a lamp. Okay. Complete figure 10.4 to show how a narrow beam of light is produced from these rays and how a spectrum is shown on the screen. Label your diagram. First of all, to create a narrow beam of light, you will create a slit like this. A small slit like this. Okay. Let me label the slit here. Yeah. This is your slit. This will cause your narrow beam of light. Now, this narrow beam of light does what? Narrow beam of light hits the prism. This narrow beam of light will hit the prism like this. Okay. I can make the beam of light much more better. This narrow beam of light hits the prism. Okay. As soon as it hits the prism, what is happening? Air is less dense, glass is more dense. What will happen? Any ideas? As soon as this beam of light hits the prism, what will happen? You are going from air that is less dense to glass that is more dense. So, as you are going from air that is less dense to glass that is more dense, what will happen? Your rays will bend towards the normal, somewhat like this. Let's make two colors, red and blue. So, somewhat like this. This is your red. Red bends the least. And let's say, this, see, this is the thing. This is a very delicate drawing to draw. Let's extend the normal. Okay, and let's make the red first of all. Somewhat like this. And then let's make the blue. Yeah. And as soon as they strike the surface, what will happen? Again, they will bend. But now, no. They are going from glass towards what? Glass towards air. Hence, they will bend away from the normal. Somewhat like this. And probably blue bends more. So, somewhat like this. You can also label that this is a red light, this is blue light, or you can say violet. Violet would be a better labeling because it will cover the entire range. And you can write web. Oh, let's do one thing. Let's zoom in a bit. Let's decrease the thickness. Let's say this is your red. Let's say this is your violet and all the colors in between. Web gear come here. Okay. This is your normal. This is your normal. This is your prism, or you can say glass prism. And yeah, I guess everything is labeled. Yeah. This normal is left. This will be a normal. Yeah. So this is how you will draw your diagram. If you draw it with a scale, it will be much more cleaner, much more suitable. And I have drawn a similar diagram in the notes as well. So you can check that out as well. Let's move on to the next. Let's move on to the next question. Let's see this. Both sounds and ultrasounds are longitudinal waves. Okay. Describe what is meant by longitudinal. Direction. One second. Let me increase the thickness. Direction of wave travel is parallel to the direction of energy transfer. Simple as that. Direction of wave travel is parallel to the direction of energy transfer. Okay. Figure 5.1 shows an ultrasound cleaner being used to clean jewelry. The jewelry is lowered into the cleaning fluid, and ultrasounds of wave 42,000 hertz are produced in the fluid. The speed of ultrasound is this. You are given the frequency, you are given the speed, you have to calculate lambda. V is equals to F lambda. V is 1500. Frequency is 42,000. What will your lambda come out to be? Let's see. 1500 divided by 4200. Lambda comes out to be 0.036 meters. Yeah, I guess that's correct. Describe how the ultrasound cleans the jewelry. Ultrasound waves. Ultrasounds hit the jewelry. This causes the jewelry to vibrate. This causes the jewelry to vibrate. Consequently, dust particles loosen up and fall. Loosen up and fall. Simple. Let's further move ahead to the next question. Both sound and ultrasounds are waves that travel in solid liquids and gases. Okay. Explain how sounds differs from ultrasound. Ultrasounds are sound waves above the frequency of 20,000 hertz. Above the frequency of 20,000 hertz. Sound and ultrasound are longitudinal waves that consist of compression and refraction. Okay, explain what is meant by a wave and describe how a longitudinal wave differs from a transverse wave. Simple. What is wave? Wave causes a transmission of energy by the vibration of molecules. Wave causes a transmission of energy by the vibration of molecules. Simple. How does a longitudinal wave differ from a transverse wave? Very simple. In a longitudinal wave, in a longitudinal wave, the direction of wave travel, the direction of wave travel is parallel to the direction of energy transfer. In a longitudinal wave, the direction of wave travel is parallel to the direction of energy transfer. However, in a transverse wave, in a transverse wave, the direction of wave travel is perpendicular. The direction of wave travel is perpendicular to energy transfer. To energy transfer. Simple as that, nothing complicated. Let's further move ahead. Figure 9.1 represents a longitudinal wave of frequency 25,000 Hz traveling in oil. On figure 9.1, mark 2 points at the center of two different rear fractions and label each one R. So this could be your middle of the rear fraction, this could be your middle of the rear fraction. Okay. On figure 9.1, draw a double-headed arrow to indicate the distance that is equal to one wavelength. The distance that is equal to one wavelength is the distance between two rear fractions or two compressions in a longitudinal wave. Okay, let's further move ahead. Part 3 is basically measuring things. So digitally, it's not possible. You can do it at home. A sound wave traveling in a liquid passes into air. Initially, it was traveling in a liquid. Now it is in a gas. Sound has a lower speed in gas compared to liquid. State what happens to the speed of sound as it enters the air. It decreases. Very easy. Okay. The wave in the liquid travels towards the surface at an angle. Figure 9.2 shows the centers of the compression of the sound wave in the liquid. Okay. Some compressions shown have reached the liquid air boundary. The parts of these compressions in the air are not shown in figure 9.2. On figure 9.2, draw the parts of these compressions that are in the air. Okay. First of all, draw normals here. First of all, draw normals here. Secondly, if you notice, if the speed is decreasing, what will happen? If the speed is decreasing, what will happen? Your wavelength will also decrease. So your waves will bend towards the normal, somewhat like this. Oh, your waves will bend. Okay, so as speed decreases, velocity will also decrease and waves will bend away from the normal, somewhat like this. Oh, let me draw it correctly. The waves will bend away from the normal, somewhat like this. Let me again try this. Maybe something like this. Waves bend away. Yeah. Away from the normal. Somewhat like this. Yeah. Waves bend away from the normal. Why? Because as the speed decreases, lambda should decrease. As lambda decreases, wavelength bend away from the normal. And if you draw it from a scale, you will also show one more thing, that the wavelength here, orange wavelength, is more compared to this wavelength. Obviously, I have tried my level best to show here, but some waves I have made too slanted. So let's correct them. Yeah, something like this. Yeah, your wavelength keeps decreasing. Simple. Let's further move ahead. Describe and outline how ultrasound is used in cleaning. So the material or object, the material or object is immersed in the fluid, is immersed in the fluid. Okay. What is the second thing that you do? Ultrasounds. Ultrasounds hit the object and cause it to vibrate and cause it to vibrate. This causes the dust particles to loosen up. This causes the dust particles to loosen up and fall. To loosen up and fall. Simple. This marks the end of past papers for waves. If you have any question, you may ask.